Good. All right, so here we are, 127. And in fact, I should say something about Canvas. I'll wait until the official time about it, though. All right. So we are here. Chapter 6 quiz today. Two of 3 and 2 of 4. Good. All right. So I've got a few minutes before the official class time. Let's take a look at the news. There's always tons of interesting news. Take care of that. Okay. And now I have to somehow get this junk off the screen. There. All right. So this one was interesting. And so is this. Might be interesting. And well, there's a few news articles and they're kind of fun. So this one here is WhatsApp, an Android app that we use in the Android hacking class, and they found a double free. So there it in a library, WhatsApp, you can send an image to somebody and they open the image in the app, and you can put malware in the image because the GIF file contains multiple frames. And it allocates space for the frame with malloc and frees it with free, but under certain conditions, you can free something twice. And if you free something twice, the result, you end up with a pointer to memory, so you can end up overwriting memory. And that makes it possible to corrupt memory, and you gain control of the instruction pointer. So this would really fit right in this class if I can figure out how to get it going. So I'm going to look into that, and maybe I can add an Android memory corruption attack to the class. This is good. Another thing I want to add to this class is .NET hacking. I found some interesting articles about .NET hacking, which I'm planning to make a lecture out of soon. So let me just make a mention about that. So here on the schedule, we're covering all the chapters and things. Today's lecture is not in the book, but it's been around for a while. I wrote one on 64-bit, and I put out a few TBAs down here for future expansion. And I've decided that one of those, I'm going to do .NET. I found a nice 3-blog series here that explains about .NET reversing. And I did some of it in the Flare-On challenge last year. Flare-On is a forensic challenge, but you can also see it as a reverse engineering challenge. And they have very good stuff. And .NET is very interesting. It's like Java and like Android apps, because you write stuff in a language like C# and you compile it, but you don't compile it down to assembly language or machine code. You compile it to bytecode, which runs in a virtual machine, and the bytecode is very readable. So it's actually much easier than x86 compiled assembly code like what we're doing here. So this will be a good thing to add to the class. And so would this be. They end up controlling the PC register, but just a carefully crafted GIF that contains 4 frames, and one of these sort of overflows into another. I don't know the details of how it works, but I'm planning to go through this in some detail and try to make a project out of it. It looks like it's not any harder than things we're already doing here, and it would be very good to see it in another context. So anyway, this I thought was very helpful because I've often wondered what to do about ransomware, and I've had my ideas. And Malware Tech has some pretty good arguments here. He says you can't just do it with backups, which is a fair statement. That's what's worrying me. I've got backups, but they're in the cloud. And if you log in with my cloud account, you can get to them. And if you take over my machine, you can go to my browser and automatically log into the cloud account. So smart enough ransomware could find my backups and delete them. And that's true of almost everybody. So like he says, there's not enough to just say you have backups. What you really have to do is have disaster recovery plans, which is a kind of big deal. You have to have, suppose, for example, the building burned down and all your computers were just destroyed totally. Then you should have disaster recovery, which means you have to have another copy of stuff somewhere far away. And that's the same thing for ransomware.
Like off-site hidden.
Yeah.
Keep it in,
yeah, off-site and somehow not accessible by an easy automatic login. That's the thing. That's why
you got to go there physically, like your laptop's a physical login.
Well, that would be one option. Would be go to physically. Another one would be to just have some kind of off-site backup in a cloud storage that there's no automatic connection to.
The way I like to do it, Sam, is have a CD, the old way, the CDs,
yeah,
and put it somewhere safe.
Yeah, for home users or people with a small amount of data, you could just have a physical drive. Of course, the problem with I realize I have the same problem enterprises have in small business. So I'm now using like a bunch of cloud services, and I have all these sprawled things all over the place, and I'm not very organized, which is true of a lot of startups. And as we hear from Carrie, as she bringing a company into compliance, this is the typical situation, and you have to really clean that up before you can meet compliance standards. Before you can have proper disaster recovery plans, you have to know where it all is, make a backup, make sure it's up to date, make sure you've got all the stuff you need to back up.
And make sure it's in synchronization.
Yeah. So, but that's disaster recovery. Anyway, so in Hong Kong, the Hong Kong protesters had an app in the iOS App Store which would record where the police are, so you can avoid getting arrested. It was like Google Maps, but it was a special app just to tell you where the police were. And so the government protested and said this app is facilitating crime, so Apple took it out of the store. So now the protesters are screaming, saying that app was making us safe, and it was just giving us access to information we should have anyway, and you rotten bums, you're a bunch of fascists causing us to get caught by the police. And so there's the screaming and yelling and blaming each other going on. And of course, this is really about the image in America. This is why Apple, I was talking to the Celebrite people when I was in Sri Lanka, and I said, I don't understand, because Apple tried to pretend to lock the cops out of your phone. So the cops couldn't, the FBI couldn't get in the terrorist phone because Apple had encrypted it, and Apple said, even we can't get in. So they just went to Celebrite, and Celebrite hacked in, because there are vulnerabilities, and smart people can exploit them, and they can totally get in. So Apple, it's not true that people can't get into your phone. It's just Apple wants to, and I talked to them, I said, it's really just marketing. They want to appear to have given you this super amount of privacy, which is more than anybody really should want. I mean, why do you want to keep the NSA out of your phone? And how do you imagine anything could keep the NSA out of your phone? You're just out of your mind. What you want is to keep criminals out of your phone and your family members out of your phone and stuff. You don't really want to keep everybody out of your phone. That's just crazy. And it can't be done at all. Because even if Apple locks themselves out as much as they can, there are still bugs, and there are hacking companies that will get in. So anyway, in the same spirit, Apple wants to somehow be like liberal and pro-protest and pro-democracy and stuff. And so I think it's all a marketing issue. If they don't want to be perceived as having acted in a way that hurt those protesters, so they may put it back in the store or something. I don't know what they're going to do.
A couple of questions.
Yeah.
So on that, so iCloud backups, it's not even encrypted, right?
Well, it is encrypted, but Apple has the keys. They have to, because the whole point of iCloud backups is if you lose your phone. Now you buy a new phone, and you have to put the data on it, so it has to be decryptable, and your old passcode doesn't mean anything. So it is encrypted, but Apple has the key. Okay. And they totally hand it over in response to a search warrant because they have it.
Oh, okay. I misunderstood what you said. It's encrypted, but it's legally.
It's encrypted, but Apple has the key.
And they have to give it to the authorities.
And they do.
Warrant.
Yeah. So if cops come up with a search warrant, they give them the iCloud data. So the only way you could protect your data from the government is to not use iCloud, and then leave it on your phone and have a passcode. And now nobody can get in without your passcode from Apple. but Celebrite can get in without your passcode. They did it on stage.
Wow.
And,
this was at Sri Lanka?
Yeah,
Wow.
and it's been sort of an open secret in the industry. They just came out for some reason at Sri Lanka, possibly because I gave a presentation where I talked about exposing all this stuff. But anyway, they demonstrated it live, and they said that was the first time they'd done that. They were admitting that they can totally hack in. They took an audience member's phone, unlocked it, and got in without the passcode, which, you know, there were vulnerabilities and they can do it, and that is their product. They can hack into anything, and they will sell that to, but not just to anybody. They will only sell it to like official law enforcement agencies of countries they approve of, because they say this is too dangerous to just give to everybody.
And it's also, it doesn't matter if you have the latest firmware update from Apple.
That's right. It doesn't matter. They can do the latest Android and the latest Apple. And when I first met the Celebrite guys in the car on the way to the conference, I asked them, can you do the latest iPhone? They said, oh, I'm not going to answer that question. And then the next day they answered on stage, okay, we can hack everything. They came out of the closet and admitted it. And they said they've been super cagey about what they can do for all these years, nervous about how they'll get in trouble or something, but they're beginning to try to be more open about what they can do. Because when the FBI did hack into the phone, they wouldn't even confirm what company did it. It was like, I think people were really worried that this would be declared illegal or something. Anyway.
Celebrite?
Celebrite, yeah. Celebrite is the main company. They're Israeli. Elcomsoft is the Russian company. It does the same thing. But Celebrite is the one that the FBI used. And I met these guys. These guys are a forensic company, and they can hack into anything. But they are careful who they do business with, because certainly if this stuff were to fall in the wrong hands, people would be stealing, because you could totally steal a phone and get in and steal the data now. And so they will only do it through official law enforcement agencies with business partnerships and stuff. But they're very famous for being the best. And so anyway, let me bring up my slides, such as they are, and I'll probably just stick mostly with the live demos here, because we're going to.
I know you wanted to show the others.
No, that doesn't matter. I'm not attached to doing all the news articles. The only point of them is to stir up discussion, so that's perfectly fine. All right, this is the wrong one. Let me figure out what chapter I do need, which is 64. I think it's lecture 7. I remember it now. Should be in my recent slides. There it is, lecture 7. Okay, this is not in the book because the book is too old for 64-bit code, but I'm increasingly incorporating 64-bit projects into this class, a lot more now than before. And so we should talk about 64 because, of course, everything is moving to 64-bit in a hurry, so we should understand it. So if you have 64-bit registers, you've got a lot more of them. You've got R, A, B, C, D. Here's the stack pointer and the base pointer. Everything starts with R because originally the registers were called like A, and that was 8 bits. And then I think AX for extended, and then EAX for 32-bit, and they finally switched to R for 64-bit. So each one of these is 64 bits wide, and then you got R8, 9, 10, 11, down to R15. So there are more total registers, and most of them serve the same purpose as before. And you can refer to parts of the register. The whole 64 register is RAX, but you can use EAX just like you would in 32-bit code, and that will be the lower half of the register. And you can have 16 and 8-bit registers too, so all those can be addressed. Although most of the time, you don't want to do that, you can. We can't see the slide. Oh, that's not right. Let me check. Thank you for telling me. It should be sharing the desktop. All right, it says it's sharing the desktop.
Is it the start video thing?
No, the video shouldn't have anything to do with it. You still can't see the slides? Let's see, another chat message is coming in. Now we can. Okay, good. Thank you for telling me. Good, I really appreciate it because I don't have proper feedback with my sort of amateur broadcasting system here. So I need you to tell me if something is wrong. If this was like a proper concert, I'd have another computer here showing me your view. Now slides are on top. Good. Okay, good. All right. So anyway, that's the way you refer to lower 16 and 32 and 8 bits if you want to. Now, for some reason, 64-bit processors don't really use 64 bits all the way through, which I found kind of a ripoff when I first learned about this. I thought that you had 64 bits of memory, so you could now address 2 to the 64 bytes of memory. But of course, 2 to the 32 bytes is 4 gigabytes. So 2 to the 64 is 16 billion gigabytes, which is an insane amount of memory. Nobody can possibly have that much memory, so you really don't need 64 bits of address space. So they don't bother with that. They only use 48 bits. for address space. So that gives you 2 to the 16 times 4 gigabytes, which is a lot. It's not as big as the whole 64-bit address. And there are different limitations in different versions. So various versions of Windows limit it more at 128 gigs, 192 gigs, 512 gigs, and so on. But that's just a Windows software limitation. And Microsoft always does this. Each version of Windows has a different amount it allows. So this means since you're using 48-bit addressing, it actually means there are forbidden addresses in all this range, and there's only 2 pieces of address that are allowed. There's from 0 up to an address 7FFF, and then there's high, which all starts with Fs. So you have 2 halves of memory you can use and a giant black hole in the middle of illegal addresses. And there's, what's that?
Sorry to cut you off. That's because Windows blocked it, or did
this is actually the way the chip is designed. This is not even Windows. This is in the hardware. This is when you buy a 64-bit processor, it's not really 64 bits all the way through. It has 64 bits of data in the registers, and it works in memory in 64-bit chunks, words, but it addresses using only part of the 64 bits. Some of them use 48, some use 56. If it was really using 64-bit addresses, then you'd be able to use all these memory addresses. But it is, in fact, doing either 48 or 56-bit. And so the only 2 addresses you'll ever see are ones that start with a lot of zeros and ones that start with a lot of Fs. All the others are not really pointing to any place you can address. So that's how it looks. Now, instead of using int80, we use syscall. And syscall is how you do kernel calls. So because one important thing about 64-bit assembly is that in 32-bit assembly, you don't have very many registers, and they're often all in use. So when you put arguments to a function, you have to put them on the stack, which is the way we got used to. You do all these push, push, push call to do assembly calls. But in 64-bit, you have a lot more registers, so now you can just use registers to move arguments into the stack. So you can have up to 6 arguments just put in these registers. Unfortunately, it doesn't use them in an obvious order, RDI, RSI, RDX, R10, R8, and R9. I don't know why they're all out of order, but those are the 6 arguments you can pass in. And you don't pass any arguments on the stack. So the system call goes in RAX. So the system calls are the ones we talked about before that kick you in the kernel. And there's a website that gives you a searchable syscall table. So here's the simplest ones. Syscall 0 is read, and syscall 1 is write. And so this is like scanf, and this is like printf. So you can call these things, and then you have the other parameters here. This is a file descriptor of where to write. And then you have a user and size. So this is the characters to write, and this is the number of bytes to write. That's how it works. So those are all your parameters. Yeah. So our syscall the same between Linux and Windows? I think they are not. I'm only talking about Linux here because this is the kernel of the operating system. This is not the hardware. So this is Linux, I think. Now, I know it is because we're going to be using it. It's all Linux, what we're talking about today. Very good question. All right. So there's details about the register here. There's a lot more if you want it. There's general purpose registers, segment registers, there's floating point registers and all that jazz. There's a bunch of other exotic registers you can use for special purposes, but we don't really need to worry about that for the stuff we're doing today. But it is also true of 32-bit machines. You may remember there were a bunch of floating point registers and there's floating point math commands. And those are mostly used for people who want to make games and 3-dimensional rotations of objects, not usually for the kind of simple things we're doing.
Like for AutoCAD?
Yeah, for AutoCAD, things like that. That's when you need fast floating point math. So here's some common opcodes for 64-bit assembly, and they're very much like what we've seen before. Move to move things between memory and registers, conditional moves, exchange, swap, push and pop, like before to put things on the stack, add with carry, subtract or subtract with carry, multiply, divide, increment, decrement, negate, compare, and shift right, shift left, rotate right, rotate left. Shift left will take a series of bits and move it to the left, and the bit on the far left is just lost. But a rotate left will take the bit on the far left and rotate it around and put it on the lowest bit, so it loops around That's the difference there. And so shift left is the same thing as doubling. And shift right is the same thing as cutting it in half, because everything moves to one bit to the right. The rotate doesn't quickly translate into any simple mathematical operation, because bits that were large roll around and become small. So it's kind of strange. But it is an option. And you've got jump and jump equal, jump not equal, and all that jazz. You have a loop command and call and return like before, NOP, and a CPU ID command. These are very much like the same opcodes we saw in 32-bit code. The only difference is they're using 64-bit registers, and if you want to get into the nitty-gritty, you have to check and see what options are available, because remember, we hit this before. You might want to add one memory location to another memory location and store it in a third memory location, but there is no command that can do that. You have to do it in stages. So copy one into a register, add the next one onto the register, take the register and put it back. So the precise details of which versions of these instructions exist are going to limit what you can do when you're writing assembly. So syscall 1 is right, and so here's how you have to do it. Set RAX to 1. That will specify that it is syscall 1, which is right. Then you have to set RDI to 1, which will determine that you're doing standard out is 1, standard in is 0, and standard out is 1. That's a C convention. And then you push the string on the stack, set RSI to RSP, set that to the length of the string, and call syscall. So let's take a look at that in assembler. Now I've got this stuff all ready to go in my Cloud Debian machine. And I added a project where you can practice this stuff. So let me just point it out, because I'm pretty much going to follow this project for the demonstration. And this is going to be 220, 64-bit assembler. So this tells you the steps. You install this thing called YASM, which is an assembler, and then you can start writing these programs. So let's start with ABC. I should have it here. And 64, okay. And so I got a bunch of stuff here. So if I nano abc.asm, tab I say, M, all right. Nope, maybe it was ABC1. It was ABC1, okay. Okay, so this is my assembly program. And let me move it so it fits on the screen a little better. I said, there we go. All right, so let's move to the bottom. Not listening to me. There. All right. So you have to define what section you're in. This is the .text section. Remember, every program has to have a .text section. That's where the executable code is. And most programs also have like a .data section, but very simple programs like this can have nothing but text. So I'm not going to have any global data. Everything is just local. You have to define a start address, because that's where it's going to enter the code. Without that, it won't know where to start running, and then it will just execute these instructions. So here, I put into RAX a fixed value, and this should be a value familiar to you by now. 41 is A, 42 is B. So just pin A, B, C, D, E, F, G, H. And you can put 8 bytes in a 64-bit register, so that's 8 bytes. So now I push it onto the stack with push. So now I just make this syscall. The length of the string is 8 bytes. The stack pointer goes in RSI because the stack pointer points to the thing I just pushed on the stack. Syscall 1 is right, and 1 is standard out, is the file descriptor 1. So now when I do a syscall, it's going to do a write to the console, which is standard out, and it's going to write that string. So let's see if this works. Now you compile it, by the way. I've already compiled this, but you do compile it with 2 steps. You use YASM minus FL64 to compile it to executable length format 64 bits. That makes 64-bit object code out of it. And then you have to link it, which we're doing here separately with LD. So this creates something called ABC1.O, which is object code, which is a executable code, but it is not yet connected to libraries. You have to link it to connect it to the libraries. And GCC did both compiling and linking, but you can do them separately. And for some reason, these assemblers are defined to do it in 2 steps. So you use YASM to do the assembly, and you use LD to do the linking. So you have to take the O code, which is object code, and create something called .out, which is going to be the executable program. And then you can run the out program here. So it's, I'll get out of here. It's .abc1.out. All right, and when you run that, here it goes. Remember what I did was I had a my parameter here was 41, 42, 43, 44. But when I run it, the letters are all backwards because this is the same thing we've seen before, little endian. If you put them for A, B, C, D, E in memory, the one on the left is the high order bit. The strings are actually read from the right. So the bytes, the characters are all here, 8 characters, but they come in reverse order. And we're used to this when you're building your strings, you always have to flip it in the words. Yeah. Okay, so then it has a segfault. Now the reason it has a segfault is we did not terminate the program correctly. We did not have an exit at the end. We just stopped running code without actually returning back to the operating system, so that's the segfault. It didn't know how to return back home. We wrote a sloppy bit of assembly code here. So let's take a look at the next one, which is ABC2. This fixes that problem. So all this is the same thing. You make A, B, C, D, E, F, you do this, and now you call exit. Just call 3C as exit. So all you have to do is put 3C in RAX, there are no other variables required, and then another syscall. This will actually exit properly. So, yep.
Because it didn't have that exit command, right?
Right. So you wrote code that just stopped and did not actually leave and return back to the operating system. So it was left hanging, so it gave you an error message. Everything is supposed to, and if you were writing in a language like C and compile it, then it would automatically add this. But if you're writing assembler, it doesn't automatically add it. It's your duty to put it in there. So this is the same thing, except it properly exits. So if I run abc2.out, that does the same thing, and then it doesn't crash. It prints out the letters out of order, and that's all it does. So I can now do a printing. Now, I guess I'll just take a look at the next one here, ABC3. I think the next problem is the letters are out of order. So I can fix that by just putting them in the order we're already used to. You start on the right, 41, 42, 43, 44. Other than that, it's the same. And so if I run that one, abc3.out, now it actually prints the letters in the correct order and doesn't crash. So I can now print 8 characters through the screen from one register by just putting them in with hex values. All right. So let's take a look at my slides and see if there's anything else I want to say that before we go ahead. So that's the ABC program we talked about. And that's the exit that had to be put in that gets rid of the crashing. And there's the one that puts the letters in order. So this is small variations on what we've already done in 32-bit. So the next thing would be to use a data section. And this is hello.asm. So let me bring it up here. So if I nano hello.asm. All right, so now let me make my window a little bigger. All right, so now I'm going to have 2 sections. Here's a text section. I'm going to add a data section. And in the data section, I'll have global variables, which are not stored on the stack and prefemoral. They're stored and available to any part of the program. And so I define a string variable, and here it is, hello world, and then a 10, which is a line feed. So this is one way that the assembler will allow us to do it to make it a little less hostile. I don't have to put in hex values for every character. It's smart enough to know that when I put it in quotes, it should take the ASCII codes for these and put them in, and then add a 10 at the end. So now I have hello world. So now I have the same kind of thing here. The length of the string is 13 bytes. Here I can, instead of pushing it on the stack and then taking ESP to point to the start of the string, I'm going to put dword string. This is the assembler. Will take this thing named string1 and find it and feed in that address, figuring that out for me. So that's good. And then I put in the same parameters. Write is 1, and 1 means go to standard out, and then syscall, and then the same old exit. So this should print that. And now it's printing it from a string section. So let's run that one. Hello.asm. Hello.out. Let's see. Let's try this way. My screen gets a little messed up because it doesn't quite know how to run nano. All right. And now I get hello world, and I even get a carriage return, so it's not just on the same line with the next prompt. So this is all pretty professional and stuff. You know what would be kind of interesting would be to do objdump minus D of hello dot out. Let's pipe it through more. This will give me the disassembly of it. And so you can see the actual codes here, and that is the whole thing. There's the text section, but there's more than a text section in there. There's also a data section. Let's try running it in GDB. And that would be hello dot out. All right, and what I was hoping to do here is, let's try info proc map. Okay, and I'm going to have to, okay, let's try disassemble. The problem is there's probably no main, yeah. There is start, let's try that, disassemble at start. Okay, so there's the code, and remember there are two sections. One section starts all with F's and the other starts all with zeros. So here's the addresses where it is. And I can put a breakpoint in here because this is going to print something on the screen and this is going to exit. So I think I'm going to put a break here at start plus 28 before it does the first syscall. So break start plus 28 and then run. And because I wanted to do this because now we can look at the memory layout of this program. So info proc map. All right, we can see how this works. So at 400,000, I've got an object file. Here's the stack. I was hoping to find where the variables are stored. And I think it must be this 601,000 is probably where the variables are stored. So let's just take a look at that area. x/10x at 0x 601,000. 601 cannot access memory. Well, how rude. Oh, that's the end address. It starts at 60,000. Okay, fair enough. Let's go 600,000. There we are. Yes, and that's what I thought. This is the part of the text. These are readable characters, so I should be able to examine them, I think, with the C format. 20C. 600,000. Okay. Yep. So that's it. ELOFOLE. I was expecting to see hello, but I'm not seeing it as clearly as I thought. But anyway, I don't want to slow things down too much, but I was hoping to find where the global variables are stored. Here's the stack. Let's look at this 40,000, see if it's there. 400,000, that is. See what's around here. Yes, here it is. No, it looks like the same thing. This is ELF. This is just the start of the ELF file. Okay. That's the start of the ELF file. It's not the stored variables. So I haven't found the stored variables. But the variable has a name, right? It was called string1 or something. Let me go back to my source code. And we should be able to find it by that. It was called... okay, it was called string1. So I should be able to examine string1. Nope, okay. Well, all right, I'm not sure how to do it in GDB. It'd be fun to figure that out. I might get it figured out by next time. But anyway, we can see a little bit about how memory is being used here. And let's carry on with the native assembly. So let's take a look at the a data section using echo. And this is going to be read.asm because we've done output only. We've been printing things out. So let's take a look at input. Okay, so here I've got a string. Now I define a global string 10 bytes long just so I have a place to put data. And then I do a syscall 0 is read, and I can read from files, but I'm going to read from the standard input, which is 0. So that's going to read from the keyboard. So this is very much like the last one, except the address, the pointer you put in here is not the pointer to the string to print, it's the pointer of where to put the data that comes from the user. So I can put in data here with this syscall, and then down here I'm going to print out the data the same way we've done before, and then I'm going to exit back to the operating system the way we did before. So this will echo. It will read something from me and then print it out. So let's try that one. That's hello, dot out. Read.out. Okay, so I say hello, and it returns back hello, and then it has extra characters at the end because I typed in hello and then carriage return, and it took that as 6 characters, hello and then the carriage return, and wrote it into the stored static string. Then it printed the stored static string, but I did not put a null byte after the input. So it had the BBCC left over from before. So this is kind of a sloppy program. It has some extra junk at the end, but it does repeat what I put in. Of course, I think I've got an overflow problem here. If I put in a lot of stuff, then it's going to have an overflow. It repeats some of it, and then some of it overflows, and the program returns, and it is passed to the bash shell afterwards because it's just sitting in a buffer. Because this program, when you write your own assembly, you don't get all the flushing of buffers and all that jazz that a high-level language like C would do. So some of my characters overflowed to the next command above. It's not the usual kind of stack overflow, though. Anyway, so that's, now the reason it didn't overflow, though, let's look at the code, is because here I told it how much to read, 0xa. So I only read 10 bytes and put it in here. So there wasn't really the typical buffer overflow kind of problem. I could possibly create that problem by changing this number. But anyway, I'm not going to bother with that for the assembly level here. All right, so that's echo. Let me take a look at my slides and see if there's anything else here to mention about it. Yeah, we looked at this. There I was able to find the symbol table with obs dump minus x. Oh, good. So there it is. That's where you can find the data section 6000 D8. And there is where you find the stored strings. In GDB, I was able to find it this way, but it was where the strings were stored, the data section for some reason not that easy to find in GDB. Anyway, all right, here's the text and data sections. I was able to print it out. So you go to 600,000 D8, and there you'll find the hello world. But for some reason, GDB does not show you where the data section is.
Is that how it's set off itself?
It probably just means I don't know the right GDB command. GDB has a lot of power and a lot of advanced commands. Like I say, I only know about the most common 10 GDB commands, and there are hundreds.
So it's finding the right one for the right.
Yeah. I found it overwhelming, so I didn't really learn everything about GDB. I just learned like the 10 simple things I need. So I'm only scratching the surface of GDP. All right, and so here's info registers that you'll see. You can see most of them are 0. Here's what 64-bit registers look like, 7FFF pointing to a stack pointer address in the high part of memory. And here's the instruction pointer pointing to the low part of memory, which has got a whole bunch of leading zeros, so that the actual instruction pointer addresses look very much like they did in 32-bit code in the range of 400,000. All right, so we did read. And so that works, but it has extra junk left at the end, like we talked about. So now we can make a Caesar cipher. So if I go here, let's look at Caesar. One, maybe it's just Caesar.as. It is. All right. So here I have a string. I reserve space for 8 characters by just making a string called string1. Now I read 8 characters from the user, exactly like we did before. So here's the length of the string. Here's a pointer to the address to put it in. And I call syscall 0 is read, that should say a 0, and standard in is 0. So this will read 8 characters from the user. Then I'm going to take that and move everything forward 1 character in the alphabet in a very sloppy manner. So what I'm going to do is take the string and put the whole 8 characters in RBX. This will move the pointer to the string in RBX. This is going to take the string at RBX and put it in RCX. So RCX will now include the 8 bytes in my string. Now I'm going to just add 0, 1, 0, 1, 0, 1, 0, 1. So it will add 1 to every byte. And that should move everything forward 1 character in the alphabet. And then I can put it back on the string by taking RCX and putting it back in the pointer where RBX points to. So now that should move everything forward 1 letter in the alphabet. Now I just need to print it out. 8 bytes, a pointer to the string, and syscall 1 to device 1 should print it out, and then I exit. So this is basically 4 lines of C going on here. So let's try that and see what happens. And this one I'd like to compile because the compiler gives an interesting message. So here is the compiling for this one. It's yasm minus f-else. Let's take a look at this one. Okay, so I compile it with this, and now it's going to warn me of something nasty, saying value does not fit in 32-bit field. So I don't quite know what that means, but it does suggest that something is wrong. However, when you get a warning, that means it still worked somewhat. You can still run it. It didn't just refuse to compile at all, but it gave you a warning that something is not quite right. So I can link it and run it. So that links it and that runs it. So I can put in a string like hello. And when I'm done, it's supposed to move everything forward one character in the alphabet. So let me make this up here to be easier to see. So the H went to I, the E went to F, the L went to M, but the O did not go to P. So it only moved 4 characters forward, not 8 characters. So now let's figure out why that happened. So we'll use objdump minus D on the Caesar dot out. Okay, and so here is the actual code. And so here is the, here's the syscall that reads 8 bytes from the user. Here is the part that actually changes the characters by adding to it. And here's the part that prints out the results on the screen. So this is the part that went wrong. And notice what happened here. That is a 32-bit instruction, not a 64-bit instruction. It only added 0, 1, 0, 1, 0, 1, 0, 1. It only did half of it, which is what we observed. It only changed 4 of the characters, not all 8. Now, the reason that happened is because the command I wanted to use here does not exist. This command right here, add RCX to this, does not exist. And that's what I mentioned earlier. You have all these things, and there are 64-bit versions, but that does not mean that every exact thing you want exists. And it turns out that the immediate adding does not exist for that. So if you go into the Intel Software Developers module, you will find add has a 64-bit version, and you can add a register 64. Now let me make this big as much as I can. You can add a register to register or memory 64, and you can add memory 64 to register 64, but you can't do exactly what I wanted to do there. What I wanted to do here was add an immediate value of 64 bits to a register, and that is not an option. You can add a register to the contents of memory, but you cannot add an immediate value, 64 bits to the register. That particular 64-bit instruction does not exist. So you have to do it in 2 steps. You have to take that value and put it in a register, and then add the register to the other register. And another thing I'd like to move into is ARM hacking. And in ARM, you have to do this a lot. Intel has a lot of versions of every instruction. You can directly refer to memory frequently. ARM pretty much doesn't. The only thing you can do with any memory location is put it in a register, then do your math in the register, then put the result back. So anyway, if you modify it to this, then that's Caesar 2. So let's take a look at that. 2.as. So this is exactly the same, except I do this shifting in 2 stages. I put this 64-bit value in register 8, and then I add register 8 to RCX. So this should hopefully change all 8 bytes. So let's try that one. And by the way, when you compile it, Caesar 2, here, if you compile Caesar 2, it no longer complains. It doesn't give me a warning saying only 32-bit byte command existed or whatever it said. It said something about a 32-byte command. So if I go here and do my linking, I have to do it on Caesar 2.0, which was produced by the previous command, and create Caesar 2.out. So I can now do Caesar 2.out. And so if I put in hello, now it goes to IFMMP, the O goes to P. So it does add 1 to every character. Now, there are some limitations to this thing. Of course, this is not a very good Caesar cipher because, for example, if I do X, Y, Z, A, B, B, C, D, E, the Z goes off the end and turns into a bracket because it doesn't roll around to A. It just adds 1 of the ASCII characters. So this is pretty sloppy work. But it did change them, and it didn't crash or anything, and it did change all 8 bytes. So I've got an approximation of a Caesar cipher here. All right. All right, so I had some challenges in the previous class. I've written different challenges for you. Before I had people writing programs and turning them in, but this time I had a different format for these flags. So down here, I've added some new challenges. So this is the improved seizure cipher. And so there are some challenges for you to solve down here. And what I did was I gave you, okay, I put, all right, let me see what's going on here. Oh, that's the part we've already done. All right, extra characters, good. So this one here, when you do seizure 2, you can get a flag there. So here's the challenge parts for the extra credit part. So I wrote a program and I removed one instruction. You have to figure out what instruction has to go there. So this one here is supposed to do another seizure cipher that moves 3 characters back in the alphabet instead of 1 character forward. So you have to figure out what to put here. And you can see this 30, 30, 30 thing here is going to change things by 3 characters. So you have to figure out what command goes there, and that's the flag. And to test it, what you should do is compile this and run it and see if you get that answer. So darkness should turn into this garbage. D goes to A, everything else goes back 3 characters, and the A turns into a greater than sign because that's 3 ASCII characters below A. Then you've got one that's a loop. These are more or less following the recognizing C constructs in assembly that we went through. So here's a loop. We've already defined a variable, a location called start. You can define a location called loop, and you can then have a jump greater than equal to loop. So if you're doing something here that remains greater than equal to 0 and eventually goes below 0, then this will loop until this thing goes below 0, and then it will stop looping. And so here's a program. This pushes 31 on the stack, which is the ASCII for 1, and this program will print 11 ones and then crash. So that's what you want. So putting the instruction missing here so that it does that. And here's another one where you define a string, bad, good. And if you printed the whole string, it would print bad, good, but I want you to make it so it prints just good. So you have to move the pointer to point to 3 characters into the string. So those are simple little things, but that's as far as I was able to go towards giving you some extra credit you could do and practice making 64-bit assembler. Now, if you look in the textbook, they actually write real shell code in assembler and then get all the null bytes out of it, and it's really pretty tedious and annoying, and I'm not giving you homework where you do that. That's what we're using MSF Venom for. But hopefully you can understand more what MSF Venom is doing this way. And by the way, MSF Venom not only does that, but then it has the option to encode it with like just alphabetical characters. So it actually has to write a decoder in front of it and encode it all. So it's pretty complicated what MSF Venom does the way we've been using it. Quite a lot more than these simple shell codes here. Anyway, let me see if there's anything else in my slides here worth mentioning. And I think not. And I don't think I have any Kahoots to go with this, but let me take a look. I've forgotten. Let me check. It'll be in my favorites, and I might have made some, but normally I have a special slide there to remind me of it. And I don't have one. So let me see if I wrote any Kahoots. 127, no, it's 126. Yeah, I don't think I have any Kahoots here. So I think that's it. I'm just going to stay around and help anybody with questions. If anybody has any questions online, just send in a chat message. All right. It looks like none are coming in. So I think I will stop the share, and I'll stick around in the classroom for a while to answer questions people may have. Okay.